G'day, in this video we're going to be looking at evidence for the existence and properties of nucleons, and our focus will be the Geiger-Marsden experiment. This video focuses on dot point 8.2.2, but also introduces concepts from dot point 8.3.1. We're still looking at the history of the development of the atom and the evidence for the atom's makeup of protons, neutrons, and electrons. This dot point is all about the nucleons, the protons and the neutrons. In particular today, our focus is on the discovery of the nucleus itself, which was achieved through the Geiger-Marsden experiment and led to the development of Rutherford's atomic model. Towards the end today, we're also going to be looking at the limitations of this model. So today's video focuses on the methods used by Rutherford, Geiger, and Marsden to learn about the nature of the atom and develop Rutherford's planetary model of the atom. We're going to outline the contributions made by their work, but also look at how there are limitations for the model itself. So let's begin by looking at the Geiger-Marsden experiment. For some context, Ernest Rutherford had already discovered the alpha particle, which we know today is a helium nucleus that contains 2 protons and 2 neutrons. At this stage, Rutherford only understood it to be a large, positively charged particle. Naturally, when you discover a new particle, what you then do is start to experiment with it. And so in some experiments where Rutherford was firing some alpha particles into a gas cloud, he observed that there was deflection and scattering of the particle beam. And so he wanted to try and figure out what was causing this. So he got 2 other physicists who he was supervising at the time, Hans Geiger and Ernest Marsden, to investigate his observations further. Geiger and Marsden were able to design an experiment where they had an alpha particle emitter, essentially something that was radioactive. They were able to fire a source of alpha particles in a beam towards a thin gold foil. And from there, they were able to observe the scattering pattern by placing a fluorescent screen all the way around with just enough of a gap to allow the beam to pass through. As such, they were able to see locations of deflections if there were any. Many particles passed through, and many also saw some minor deflection. However, there were observations of some particles essentially getting knocked back, having a deflection beyond an angle of 90 degrees. In other words, the alpha particle never crossed the metal foil. These results were quite surprising and did not match the hypothesis of these 3 physicists. By this stage, the Thomson plum pudding model was widely accepted, and as such, they predicted that the radiation would be able to quite easily pass through the foil. Their reasoning being that according to the model, the atom itself contained very low density matter throughout the entire atom, meaning that the alpha particles would quite easily be able to pass through as they were quite dense and were moving quite quickly. The hypothesis did account for some interactions with electrons, which may have caused some deflection, and as such, the minor deflections may thicken the beam at the end slightly. What they observed instead was this. And there's quite a famous quote by Rutherford, which really does speak to how surprised they were about this result. It was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it had come back and hit you. With the current understanding of the atom and the implementation of Thomson's model, it seemed to be impossible that there was any material inside the atom that would be capable of deflecting the alpha particle source in any great means. What this suggested was that Thomson's model was imperfect, and there needed to be an explanation for the difference in results and a failed hypothesis. As such, Rutherford tried to develop a new model with features that would explain the observed phenomena. By quantitatively analysing the results, the conclusion was that there must be a small, dense, positive nucleus, and therefore, when the alpha particle came into contact with the nucleus, there would be deflection caused by a Coulomb repulsion. This accounted for all observations. The majority of particles were able to pass through the foil because they never came into contact with any particle at all, simply because the atom was mostly empty space. Some particles experience a minor deflection as they pass closely to the nucleus itself, and therefore were deflected along the way. However, others were deflected more than 90 degrees. And this is because the path of the alpha particle was directly in line with one of the gold nuclei, meaning that it had nowhere to go. This repulsion was therefore also strong enough to completely deflect it and knock it back. This model was known as the planetary model of the atom and included the following key features. that the atom contained a dense center called the nucleus, and that the volume of the nucleus was about 10 to the 15 times smaller than the volume of the atom. Think a marble inside a stadium kind of scale. And even though the nucleus was so small compared to the atom, pretty much all of the mass existed in there, apart from the electrons, meaning that the rest of the space was completely empty. They also knew that the nucleus was positively charged. To account for the electrons, they suggested that the electrons orbited the rest of the volume in the atom. Essentially, they moved in circles around the nucleus just like a planet would, thus the planetary model. Even though this model was a vast improvement on J.J. Thomson's plum pudding model, there were still some significant flaws. Rutherford was not able to identify the composition of the nucleus. He just said there was lots of matter and it was positively charged. Another issue was the electron. The electron itself had to be somewhere. And if there was a dense positive mass in the center and the electrons were just simply existing in free space, we would expect to see that the electrons would collapse in towards the nucleus due to Coulomb attraction. And as said before, to address this, Rutherford suggested that they were simply just orbiting the nucleus like a planet. Except this came with issues and a lot of pushback. Scientists at the time implementing simple classical physics knew that the particles had to have a centripetal acceleration which was caused by electrostatic forces. But they also knew from their understanding of electromagnetism that any charge that was accelerating would emit electromagnetic radiation. If that was the case and radiation was occurring, the electrons would be losing energy. And if they were losing energy, they'd be losing velocity. And that would just result in the electrons collapsing into the nucleus anyway. So even though Rutherford's model tried to explain how the electrons would behave, it still wasn't enough. What's important about this model, though, is that the model continued to develop once observations occurred that seemed to refute Thomson's original model. And further to that, the holes within the model only prompted questioning from other scientists who were then able to investigate the issue further and learn about the nature of the atom at a much deeper level. In our next video, we're going to be looking at some work that was able to resolve at least one of Rutherford's issues. What was the composition of the nucleus, leading to the discovery of the proton and the neutron? Until then, have a good one.